Okay, so we're recording. Last time we finished section 3.3. Off we go to 3.4. So this is going to be a weird section. All of the stuff in here, frankly, is pretty premature. I know why Kali put it in here at this early stage in the course, but there's a real pro and con situation here. So starting with the pro, the advantages of introducing this material here are that it takes some ideas that are going to be important and hard to digest from chapters 6 and 7, and we plant these thoughts early, and that gives you an opportunity to kind of start chewing on it, kind of start getting used to it. And then when we get to it in 6 and 7, it's not so much, right? It's you're less likely to choke on it. So here's the downside. In order to really make sense out of the stuff that I'm going to be telling you in section 3.4, I mean, we really need to have a bunch of other stuff set up. I mean, the context and the tools that are necessary to understand this, we just don't have yet. So it's going to be very out of context. It's going to be a bunch of completely unmotivated assertions that I'm going to be making, and as a math teacher, I don't like doing that. I like stuff to be motivated. I like it to make sense. I like it to come up naturally. So we're not going to have that in section 3.4. Apologies in advance. It is what it is. I'm going to do it the book's way because, well, we're following the book, and I think it would be problematic to not do that. Okay, so here we go. All right. Y'all remember the gradient? Of course. Here's a kind of a quick rewrite of the gradient, the idea being that we're going to take all of the various different partial derivatives that we're going to take. We're going to kind of remove the operators. It's what we call operators. I'm going to pull those out away from the function and write the operators themselves as a vector, as if you can do that. Right? And that's a little weird and uncomfortable perhaps, but nevertheless, if I do that, if I view that little triangle itself as being sort of a vector of operators, something that's being applied to a function f, right? Green acts on blue, as it were, right? Well, then it's the same thing as still the same formula for the gradient, but now I have this new object, this independent thing that we're going to call the del operator that I can talk about and do other things with. Now, a lot of students look at this and they think, why wouldn't we just call this the gradient operator? After all, that's what we do with it, is we compute the gradient. So it seems like this ought to be called the gradient operator. Very importantly, this is not all that we're going to be doing with this operator. We're going to be doing actually a bunch of stuff with this thing. You'll see momentarily. Yes, we are still going to use it as a notation for the gradient. We will also use it in different ways. So you can't call this the gradient operator. It just doesn't work. So heads up about this. This is called del. Okay, so that established, here's the very first thing we're going to do with it. It's a notational convenience for talking about this thing called divergence. What is divergence? I'll tell you in a minute. Where does it come from? I'll tell you in a few months. Right? It's going to take a while. Again, no context. This is highly premature. But here it is. Here's what it is. The divergence of a vector field is this formula right there. That comes out of nowhere for no apparent reason. Okay. Now, what you're going to notice about this is as something that is applied to a vector field with coordinates f1, f2, and f3, it's almost like I take the del operator that you see here, partial with respect to x, partial with respect to y, partial with respect to z. It's almost like I'm doing a kind of a dot product because I'm applying the first coordinate of del to the first coordinate of f, second coordinate to second coordinate, third coordinate to third coordinate, and then adding them up. It looks like a dot product. So the formula for divergence is this thing over here, and this notation to the left, del dot, is to be fair, a little bit of an abuse. It's not really how we've defined dot product. Previously, we've defined dot product as literally something you do to vectors. Del is not really a vector as we've understood them to now. So a little bit of an abuse, but you can see why the notation is really handy, right? It really looks a lot like that. So this is what we're going to call harmless. It's a reasonable choice of notation. It's extremely convenient, as it turns out. And for whatever it's worth, in my physics days way back when, I saw this notation for divergence more than any other. So this is very standard. It's very typical. All right, so weird though it is. All right, so why do we care about this thing called divergence? What does it do? Divergence, namely this formula, well, as I previously apologized, I don't have the context. I can't motivate this. All I can do is make an assertion, completely unmotivated assertion, and that is this right here. Roughly speaking, whatever vector field F you're talking about, the divergence kind of suggests to what extent is fluid flowing outward away from wherever it is that you're evaluating divergence. Okay, so now let me just draw a picture and give you an example. Here we have a vector field, and we've already seen this vector field previously. Drew that picture, something very similar anyway. And you can see that if this were to be representing a fluid, I mean, it really is. It looks like the fluid is flowing outward, sort of away from, let's say, the origin. We'll focus our attention on the origin. Does the divergence capture this? Does the divergence do what it says? Well, divergence is this formula. Right, x partial of the first field component, y partial of the second, z partial of the third. Easy partials, easy arithmetic, and notice we get a positive divergence. So positive meaning yes, to a positive degree, the fluid is flowing outward away from the origin. Okay. All right, so this is the, I'm going to say, kind of the easiest possible first example of what divergence looks like. There are other sort of versions of this and more complicated cases that we're going to talk about later. That's a chapter 6 and 7 thing. For the moment, I just want to point out that this tracks, right, with the claim. I mean, it doesn't prove anything, but this is what I mean when I say that divergence represents a fluid kind of flowing outward away from a given vicinity. Okay. Now, a quick digression to talk about physics. What does this mean about the fluid? What does this mean about related things, things related to what's happening here physically? And I want to point out there really are two different takes that you can make of this. Perfectly reasonable. One is, let's imagine that we're in the ocean and this flow right here, not the water. Water can't do this, right? That'd be weird. How would the water all flow away? You can't do it, right? But let's imagine that this represents the sort of the flow of fish, right? So this, we've talked about how large groups of animals can be thought of as a kind of a fluid in a way. And so if this is what the fish are doing, I would propose that this means that the number of fish in the general vicinity of the origin is decreasing because they're swimming away from there, right? If they're swimming away from there, there's less fish remaining. Pretty believable. Okay, so given that interpretation, a positive divergence should represent a decreasing density. Stuff leaving means less stuff remaining. Okay, so I hope that's intuitively satisfying. Now, here's a completely different physical scenario. Just as valid. but a totally different physical scenario where this would be a vector field, and we're going to make a completely different interpretation. So imagine that instead of fluid of fish, imagine I have a light bulb right there. Right? Nice bright light bulb. Well, that's going to be shooting photons outward, kind of like what we have in this picture here. Not exactly, this isn't exactly right, but something along these lines. Now, what physical take would I walk away with if I said that there was a flow of photons, right, like this, coming from a light bulb? Would I suggest that there is a decreasing number of photons? No, absolutely not. You're not losing photons. Light bulbs don't come with a finite number of photons, and then when they run out, that's not why light bulbs die, right? Light bulbs generate the photons. They make them as they spit them out, right? So the takeaway that we would have here, it's got nothing to do with a decreasing density. You're not losing photon density. You are creating photons. Right? So now note these are very, very different physical interpretations that all come from the same picture, that both come from the same positive value of divergence. So again, I just wanted to plant the thought here, right? And by the way, it's worse than this, because not only are these two possibilities, there's also a possibility that the kind of fluid that depends on the fluid could be a combination of these. And that's something that you would study more carefully in other classes, I would imagine, like fluid dynamics or something like that. So anyway, make sure when you compute a divergence and you get a value, positive in this case, you want to make an interpretation of what that means physically. You got to think very carefully about what kind of a fluid is this. And if it's the kind of a photon-like fluid, then you've found a source of fluid. And if it's more a stuff-like fluid, then you found a place where the density is decreasing. Okay. All right. Okay, another example. This is a quicker one. Vector field picture. By the way, make sure that this makes sense. If you need to spend a little time after class to sort of think it through and why this formula gives rise to a picture that looks sort of like this, take the time as necessary. Reminder, you can always come to office hours. Happy to help. But make sure you're comfortable if that's a reasonable picture of this vector field. And in fact, make sure that you could produce a picture like that from this formula, just kind of thinking through what that means. Okay. That said, let's compute the divergence. There's how you compute the divergence. You note that it's 0. What does this mean? Keeping in mind that divergence are what we've been told baselessly, right, for what divergence is. It represents how much the fluid is going away from a general vicinity. Well, the 0 should mean that the fluid's not really going away from anywhere, right? So notice that this is 0 no matter where you look. So for example, if I were to consider a vicinity about like that, in the net, the fluid's not flowing away from that point. Now, some fluid is, right? There's fluid right there that you can clearly see is flowing away from that general vicinity. But as you can see over here, there's just as much fluid flowing in to that general vicinity. And I'm going to appeal to your intuition for this kind of thing. There's just as much going in as there is going out. So in the net, there's really not a outward flow of fluid away from that area. Does that make sense? Okay. So I'm going to say this tracks also, right? No net outward flow of fluid, no divergence. Okay. Alrighty. Next one. So another definition that I'm going to make, again, for the purpose of allowing you to kind of let these ideas start rolling around in your head and settling in and getting comfortable Nice to have let some time contribute to that. We're going to make a better presentation of this when we get to Chapter 7. Until then, here's just a formula and a baseless assertion. We're going to define this thing called curl, computed by this formula. Notice this is actually kind of like a cross product. Remember, a cross product is where you take a determinant where you have the standard basis vectors across the top row. And this is pretty literally a cross product then of the del operator with some vector field F. All right, so kind of neat that the curl is literally a cross product. Okay, well, maybe not as an abuse of the term literally. It is symbolically, anyway, a cross product. Right? Again, del, not really a vector as we understand it. Okay. All right, now you can take this formula for curl, this formula for this cross product looking thing. You can take this determinant and actually kind of crank it out and write down all of the terms for all of the coordinates, and there's quite a bit to write down there. You should probably do that at some point. It's a good, healthy exercise to make sure you get it right. The eventual formula is in the book, and you can check with that. For whatever it's worth, I've never memorized that formula. I've never needed to memorize this formula. It's a lot easier to memorize this, right, the way it's written down like this, because it's just easy to remember, okay, del in the second position, F in the third position, and I know how determinants work. Okay. Okay, so why is this interesting? Long conversation to come in Chapter 7. What is the punchline? Baseless or otherwise. The punchline is that curl, namely this thing, it's in a way telling us how the vector field is representing a fluid that has what I'm going to loosely call a rotational aspect to it. I'm being deliberately vague. It's actually pretty delicate how to define this, and it's really, you can really only define this well with formulas involving tools that we haven't talked about yet. So I just can't give you a really good definition of what I mean by circulation. But it to some extent means that there is a rotation in the motion of the fluid. Okay, so specifically the curl vector tells you two things. It tells you how much of a rotation there is. Are we talking about a Category 5 tornado? Or are we talking about a gentle kind of, stirred, bowl of soup? Right? Very, very different things. So the magnitude of the curl is going to tell us how strong of a rotational aspect there is to the fluid. And by the direction of the curl, it tells us the axis that the fluid is rotating around. Again, let me just give you an example to help you see what we're talking about. So as previously discussed, we know what this vector field looks like. Now this is a slight variation of the one that we actually talked about. The one we actually talked about was in R2. You'll notice this is in R3. But notice also that it's really just this counterclockwise rotation of fluid. It's a stirred pot. Right? The only difference being that instead of only talking about the very top surface, here you can see this is the horizontal counterclockwise rotation of fluid at all heights within the pot. For every Z, no matter how deep the pot is, it's all sort of flowing around in this same way. Okay, so basically the stirred pot. We can compute the curl. Various partial derivatives to take, and you punch this all up, and you get this 0, 0, 2. Now, what are we going to do with 0, 0, 2? What does that tell us? Well, here's 0, 0, 2. And notice, 0, 0, 2 defines an axis. I can do better than that. That defines an axis. And notice that our fluid, as promised, has a sort of a rotational aspect of sorts around that axis. So the curl, by virtue of which direction it points, tells us the axis that the rotation is going around. How we doing? Everybody all right with that? No justification. Don't look for a reason why. This is just a claim. Yes.
Is this curl only defined for vector fields in 3 dimensions?
Yes, that's right. It is a peculiarity of 3 dimensions. Yeah, absolutely. Which kind of sort of follows from the fact that cross product is a, yeah, exactly. Right. Exactly. Okay, now let's talk about the magnitude here real quick. In some sense, the fact that the magnitude of this vector is 2 is telling us something about how much of a rotation, how hard did I stir the pot? Now, in what way do I quantify that? Well, that's a long story, and it's ultimately really not something that we're going to worry about in this class. We're not going to make up units of stirring, right? So all I'm going to say is the longer the curl vector is, the more of the rotation is happening. Okay. All right, so that's our first example. Now let me also show you an example where there is none, right? So another easy little scenario. And again, make sure you can use that formula to generate this picture of that vector field. Something to think about there. And you can look at how the water flows, right? Find the flow lines for one thing, right? And the flow lines are doing kind of like this, right? Doesn't appear to be any rotation going on there. If you just look at this picture, your guess would be that the curl would be 0, and you'd be right. So, no rotation, no curl. Everybody good? All right. Now, we will eventually make a proper definition of circulation. We're not there yet. We don't have the necessary tools. Until then, I do want to point out a common misunderstanding. The common misunderstanding is that when I talk about the rotation of the fluid, that I'm talking about individual pieces of fluid and how their flow lines have a curvature to them. That is not it. It's not about any individual piece of fluid and it going in some sort of a circular path. It's an overall thing about the fluid as a whole. And again, definition to follow later. Not, we don't have the tools yet to make that precise. But I just want to show you this example, just to show you how flow lines are not the point here. Right? So here is a vector field. There's the picture. Again, make sure you can not only persuade yourself that this is a plausible picture, but make sure that you can generate, right, from the formula a plausible picture of what that looks like. And we look at the flow lines, and the flow lines are all straight lines, aren't they? And there is a temptation, looking at this picture, to say, I don't see any flow lines curving at all. There's a temptation to say that there's no rotation happening here. I claim that there is a hidden rotation. Again, it's not about individual pieces of fluid. It's about the fluid as a whole. And I point out that if this were representing the way water is flowing in a river or something, maybe you have 2 rivers that kind of meet and they're kind of go in different directions temporarily. I don't know, whatever, right? If you were to drop a leaf into the river right there, well, it's going to be being pushed that way on one side and that way on the other side. It's being pushed in what you might call opposite directions. I would point out that it's being turned clockwise on both sides. I think this leaf would spin sitting in the water there. Does that make sense? So no individual piece of water is turning, but the leaf is. So that's what I'm going to call kind of a hidden rotation. And notice, the curl detects this, right? The curl gives you a non-zero value. So the fact that this is non-zero picks up that there is a rotation story in this picture, even though the flow lines don't detect that at all. Everybody on board? Okay. So circulation is not flow lines. Make sure to keep that in mind. And by the way, I'll give away the game on there's a homework exercise that's going to come up later in the course that turns on exactly this point. Roughly speaking, I don't want to give away too much, but it's something to the effect of a seeming contradiction that is observed, and how do you resolve the contradiction? And the contradiction is that in the statement of the question, there's this assumption made that curl has something to do with flow lines, which is just not true. All right. Okay, so moving along. We are about to venture into some really deep water. I am very much not going to be able to tell you the whole story on this. It's way beyond what's plausible for a class like Math219. The ideas I'm about to point out actually weren't even known until less than 100 years ago. This is modern, recent, very sophisticated math that eluded some of the best mathematicians in the world for decades, right? This is really, really deep stuff. So now I'm not going to tell you the whole story. It's way too much. I'm not going to give you all the formalities and technical definitions and rigor and no. I'm going to boil all that off. I'm going to give you just the bones. What's the punchline? And the punchline is, good things happen when you compose these three operators. We have the gradient operator. The gradient, of course, takes a function and produces a vector field. We have the curl operator, which takes a vector field and produces another vector field. And then we have the divergence operator that takes a vector field and produces a scalar valued function. Okay, and when you compose them like this, mysteriously good things just happen for reasons that, again, are very sophisticated, very cool, and not at all appropriate for this course. So, again, I just want to show you what some of these cool things are. I want to try to persuade you that it's in your best interests to think about these operators put together in this way. Even if you don't know why, it's very valuable to know that they should be thought of as composed in this order. All right, so here's what the cool punchline is. This is what we call an exact sequence. There is an asterisk here. The asterisk, confession that yes, there are some little trivial counterexamples. Let's not worry about the counterexamples. Let me just show you the big picture. The big idea is that everything has a lifetime of 2. What do I mean by that? Example. If you have a function and you take its gradient, right, taking a gradient of some function down here. If you then take the curl of whatever is produced, you will get 0. This is what I call a lifetime of 2. Don't overthink the metaphor, right? It's just a metaphor. It's not precise, but born here, dies here, lifetime of 2. You know what I mean? I mean, so again, there's no need to get strict about it, but there's 2 steps until it died. Okay. All right. Here is another version of that. And again, the idea is everything has a lifetime of 2. If you have a vector field for which the divergence is 0, I don't need an exclamation point there. If you have a vector field for which the divergence is 0, as we presume here, then it turns out that that vector field must be the curl of some other vector field. So now there's a temptation. Without this observation, there'd be a temptation to say, "Haha! Look at this! I found something that dies immediately." Right? This thing here, I took its next step in the composition, and if I did the operator, I got 0. Lifetime appears to be 1, but it isn't, because this isn't where it was born. It was the curl of something else. It was born here and died here. Lifetime is 2. Like I say, it's really weird and surprising that this always works. Again, very few silly little counterexamples, and the broad point is what we're focusing on here. Okay, how are we doing? Now, I want to emphasize there's no way that you could possibly have any sense for why this is true. Don't look for that explanation. You're not going to find it. Right? I just want y'all to know that it's true. I want y'all to be persuaded that, hey, it really does make sense to kind of put these in order like this, because these unbelievably convenient coincidences just always work out. So as you absorb the ideas of chapter 6 and 7, mostly 7, as we go through these stuff, I strongly encourage you to just in your mind be thinking about these things organized in this way. And I'll be doing that myself with the diagrams I'll be drawing on the board when we get to chapter 7, things like that. But just wanted y'all to be on the lookout for these kinds of facts. So this and more. There's just lots of relationships between gradient, divergence, and kernel, and a tremendous amount to say about it. And that's pretty much what the content of chapter 6 and 7 is. Okay. All right. So that does it for chapter 3. We move on now to chapter 5, not 4. Real quick, let me talk about that. So here's one of the hard things about teaching a multivariable calculus course. That's the vector calculus material, subject of chapter 6 and 7. It's very challenging. There's lots of ideas. There's lots of connections. There's lots of geometric pictures to absorb. There's just a lot going on in chapter 6 and 7, right? So that's the most challenging material in the course. That's what we need to really settle in on and spend the most possible time on. When you have hard ideas, it's good to have as much time as possible to absorb, to kind of let those ideas roll around and kind of get used to it. If it were possible, I would start this course with chapters 6 and 7. But it's not possible, because the stuff we're going to need to do in chapter 6 and 7, it relies on chapter 5. It relies on chapter 3. It relies on 2 and 1. It relies on all the chapters that come before it except for chapter 4. Right? So I can move chapter 4 to the very end of the course. Doesn't cost anything. And the benefit is that gives us a little bit, I get to do chapter 6 and 7 a little bit earlier. Not a lot earlier, but a little bit earlier. And that extra little bit earlier gives y'all that extra little bit of time to digest it, which is going to help you digest it better. So that's the big idea. We will come back to chapter 4. We're just going to do it at the very end of the course. Okay, so that said, here we go, starting with integrals. Quick reminder, wrong tool here. Quick reminder, when we were talking about derivatives, chapter 2, we started with partial derivatives. After I noted there's something awkward about that, right? Partial derivatives are easy, they're relatable, but they're really not how you should think about derivatives. And there's a point of view that says you should always start with what you want to be the central, fundamental point of view you want students to have in a given subject. And partial derivatives are not that fundamental point of view. What we saw very quickly, and y'all know now, that the fundamental point of view about derivatives is that, look, there's input changes that are velocities. There are output changes that are other velocities. And a derivative is a relationship between input vectors and output vectors, and the way you relate vectors to vectors is with matrices, right? So fundamentally, derivatives should be thought of as matrices. That's the big takeaway from chapter 2. So it's annoying that I had to start with something different that's really kind of a distraction from that. But again, I have to because the book did. I have to because of just what's realistic. If I had started off, day one talking about derivatives as being matrices, you wouldn't have liked it, right? So we're going to do something analogous here. I'm going to start this discussion of integrals with, again, something that's really not the best point of view. I don't want y'all to think about integrals in the way that I'm about to show you at the end of this course. But what I'm about to show you is the obvious, natural first step, and so it's just much more relatable to do it the way I'm about to do it here. So again, just make sure that you don't plant your flag and set your cornerstone for how you think about integrals based on what we're about to do. This is a first attempt, and we're going to find something much better Friday. Okay. All right, so flashback, single variable calculus. Y'all remember all this business here. If you have a rotated surface like so, right, you want to compute the total volume inside of that rotated surface. The way you compute that volume is by slicing it up into pieces, right? We're going to consider one little piece at a time. That little piece there has some volume. I'm going to then add that up over all values from A to B. And that little piece of volume itself is a thickness, right, a little thickness there, dx, times a cross-sectional area, right? And if I look at that cross-sectional area there, it's just the area of a disk, pi r squared, blah, blah, blah details. Everybody kind of remember that way back when? Right? Okay. Cool. Okay, so a volume can be chopped up into little pieces and added up to result in the formula that y'all have all seen before. By the way, I think it's a pretty good point of view on integrals in general. An integral is where you take a quantity that is a whole and you view it as being the sum of a bunch of individual parts. So integrals are the case that a whole is the sum of the parts. It's a very elegant way of thinking about it, I think. Okay, all right, let's try to take this point of view on a different question. So now on to, this is a truly multivariable question. Notice I am looking at a graph. Y'all know I think it's really important to make that emphatic distinction. I have a graph of a function of two variables. Right, so there's my domain, as it were, is two-dimensional. Looking at that graph, the graph is this surface up here, something like that. Depends on the function. I could imagine being given a rectangle down in the domain, and perfectly reasonable question. In the same sense that you can ask how much area is there under a curve in 2 dimensions, we're going to ask here how much volume is there under this surface in 3 dimensions. Everybody see how this is a natural sort of extension of the single variable version of this? Is everybody happy? All right, so how are we going to do this? Well, we're going to rip off the idea that we were just talking about. The whole is the sum of the parts. I'm going to make a bunch of slices. I like to think of this as a weird-shaped loaf of bread, and I argue that the volume of the whole loaf is the sum of the areas of the slices of bread. So that's just a fun little metaphor. How am I going to compute the volume of one of these? Well, just like I did above, I'm going to look at one of these by itself. And I'm going to say, well, it's a thickness times an area. And the area, that's, up here, the area was a garden variety geometric figure that we knew from 9th grade geometry class. And, you know, the area of a disk is pi r squared, right? Nice, easy little formula. I don't have any garden variety high school geometry formulas for what this cross-sectional area is. It's not a disk. It's not a square. It's not a rectangle, triangle, parallelogram, rhombus. It's nothing. Seems like we're dead in the water. Yeah? So, we would be, except for the following observation, and that is this cross-sectional area that we need here is the area under a curve. Oh, I just circled the wrong thing. It's the area under a curve, this curve. Right there. Area under a curve. We know that. We know how to compute area under a curve. Right? Okay, to clarify. We know how to compute the area under a curve that's a graph. So is this curve a graph? Well, yeah, in fact it is. Because look at this curve. Here's the equation for that curve. Z is f of x comma y. But notice y is fixed. Right? We're looking at the cross-sectional area at one value of y at a time. Right? When you're writing down the volumes of little slices of bread, you got to pick a slice of bread first before you can talk about what the area is. So you pick a slice, fix the value of y, in other words, and with y being fixed, y is now a constant. How about that? We have z, height, as a function of x, which goes that way, and sure enough, height, z, is a function of one variable. That's a graph. Is that cool? So area under a graph? Yeah, sure, no problem. Area under a graph is just that integral. Now, notice we have to pay careful attention to what x is doing, right? We're only interested in what's happening sort of for these values of x. Right there, right? So x goes from A to B. And as we're computing this area, the little widths of these little pieces of area, the widths of these little strips of area, dx. Right? It's a width in the x direction. So dx. Everybody on board? And at this point, it's kind of all over with the shouting. We just have to kind of put the pieces together. So altogether, we argued that the total volume is the whole is the sum of the parts. I just have to look at each little piece of bread and add them up. Right now, those parts, how big is any slice of bread? Well, volume is area times thickness, as previously argued. Area, we just got through arguing. Missed. Area is that dx integral. So dv is all of this business. Again, it's just area times dy. And altogether then, our actual total volume, the original, let's see here, how am I going to do this? The original total volume back here is this expression right there. And what's weird about this is an integral of an integral. It seems kind of creepy. Wait a minute, which direction are we going as we're doing this integral? We're going both directions. Because on the one hand, I'm looking at y going from C to D, because I do, in fact, have to look at all of these individual slices of bread, right? I'm adding up in the y direction, I'm adding up the volumes of each slice of bread. That's the dy integral. But in order to compute each one of those volumes of slice of bread. I need to know the areas, and the areas are what I get as I do chop it up, add it up, whole is the sum of the parts concerning these areas in the x direction. That's this inside. So, integral of an integral. Pretty weird. Everybody okay? Okay. All right, so for whatever it's worth, this is called an iterated integral. The idea there is probably pretty clear. We're doing an integral of an integral. We're repeating the integral, thus the term iterated. This has always bugged me a little bit, though, because they're different integrals. We're not doing literally the same thing twice, as would be suggested by the word iteration. This is an integral inside of another integral, a different integral, different variable, different bounds. They're different. So I've always been a little annoyed at this term. I tried to popularize the term nested integral, which I think, because it's literally an integral inside of an integral, like Russian nesting dolls. I thought that made sense. Didn't catch on. Oh well. So you're going to hear everybody else say iterated integral. Do be careful with the terminology a little bit. There's a temptation to talk about these integral as being the first and the second. Which one's first, which one's second? As we constructed them, we wrote down the dy integral first, because the very first thing we did in trying to compute our volume was we chopped it up into slices of bread. That was the first thing we did. So the dy integral is the first in that sense. But when it comes time to actually compute these iterated integrals, you can't compute the dy integral first. If I wanted to do the dy integral first, I'd need to take an antiderivative of the integrand. The integrand, I don't know yet. I don't know the dy integrand until I do the dx integral. So unavoidably, when it comes to evaluating, I have to evaluate the dx integral first. So this terminology, the idea that we can talk about one of these integrals as being first and the other one second, it's very ambiguous. Doesn't really make any real unambiguous sense. So please don't use terminology like that. Please don't talk about the first and the second. I don't know what you're talking about. What you can do, and I think this is easy, is you can talk about the inside integral. That's perfectly clear which one's on the inside, right? And you can talk about the outside integral. Again, perfectly clear. So, gotta think that through. Okay. All right. Last thing I'm going to point out while we're here, before I get on to an example, which I hope we'll have time for. While you're doing this inside integral, don't lose track of what you're computing. For this inside integral, what we're computing is this cross-sectional area. That cross-sectional area only makes sense for a specific value of y. Said differently, the outside variable, while you're doing an inside integral, the outside variable is constant. It has to be. Right? That outside integral has to be constant. Otherwise, I don't even know what area we're talking about. Right? So while you're doing the inside integral, the outside variable has to be viewed as a constant. And let's see, how are we doing on time? Oh, I have a watch. I don't think we're going to have time for this example. I tell you what, I'm pretty sure I owe y'all at least the 48 seconds we have left. We'll draw the line right here. This is a pretty reasonable place to draw it. And we will pick up here on Friday. Y'all have a good day. See you later.